So we're going to graph these by hand, and then if you're thinking, well, does Desmos graph piecewise functions? The answer is yes. And then you're thinking, well, then why don't you just show us already? And the answer to that is, I'm going to be honest, I don't remember how. If you're like, man, we'll just look it up. Here's the deal. When you type these into Desmos, you're going to have to type a whole lot of stuff that involves punctuation that I honestly don't remember. And I have taught it in the past, but people don't remember, like, where does the colon go? Where's the comma go? I will show you in another video, but I'm not going to show you yet because we still have to have the skills without Desmos. For example, we need to know when to fill in a circle and when to leave it open. So I'm going to pause what I just said and tell a completely random story. Several years ago, and I mean like 20, my parents ran into my elementary school principal and he said, "How's Adam doing?" And they were like, "He's fine, he's teaching, blah, blah, blah." He said, "Tell him I said, hey, and give him this." And I have had this pencil for forever. Mr. Williams caught me being good. Actually, he didn't catch me, he caught my parents. But anyway, caught me being good. I got a pencil. It has been unsharpened for 20 years, and I am just now breaking it out. There. Sorry I wasted a minute of your life telling you that. Okay, let's graph with a 20-year-old pencil. If you don't have a 20-year-old pencil, grab one. I'm using a pencil and not an ink pen, and the reason why is because I like to graph these and go a little too far and then be like, oh no, I made a mistake. You'll see what I mean. Okay, let's graph the function -4. So -4 is simply, well, -4, and this is really y equals -4. So that's this. It's a horizontal line. Oh no, I graphed too much. So because this is an old pencil, I don't know how good the eraser is going to be. So I have another eraser. Here's what I really want to graph. I wanted to graph -4, but I need to restrict its word you're going to learn later, domain. You've actually heard the word before, but you're going to hear it in a different context later in another lesson. But what we're going to do is restrict the domain of this -4 from -5 to 0. So my x values are restricted from -5 to 0, so only what you see here is going to count, which means I graphed too much. Now, yes, you could totally do this with an ink pen as long as you're careful, but I like the demonstration aspect of being like, oh, this is what I need to keep and this is what I need to erase. Excuse me. So I will not have my function equal to -4 when x is -5. So open circle here. I will not have my function equal to -4 when x is 0. Notice I don't have an equal sign here or here. So open circle there. And this graph looks like that. So if I handed you this graph and I said, hey, what's f of -2? You'd be like, oh, -2 is there. Or you could use the equation, either way. All right, let's graph this guy right here. Second part. 1/2 x minus 3, it's a line, slope-intercept form. There's your mx plus b. Your y-intercept is -3, so 1, 2, 3. Put a dot right there. Slight dot. Slope is 1/2, so up 1 over 2, up 1 over 2, and we graph. And you can graph and go crazy with it, and you can be like, look, I'm graphing, man, I love graphing. And then you'd say, oh no, I graphed way too much. So let's restrict this. Let's restrict the domain of this portion. Domain is the x values. Again, you've heard the word before. You'll hear it later in a different context. Slightly different context, different notation. And so we're going to restrict it from 0 to 3 on the x-axis. So I'm going to keep everything between 0 and 1, 2, 3, and everything that you don't see from this graph is going to get covered up or erased. So everything that was covered up is getting erased. There we go. So from 0 to 3, and I will keep this, but I'm going to erase everything else, and I did erase it mostly. Not without eraser. And I need to look at the equals or not equals and determine if I have open or closed circles. So where x equals 0 for the diagonal line, I am equal, so circle, fill that thing in. And at 3, it is not equal. So if, again, if someone handed you this graph and said, hey, find the value of the function at 4, you'd go over to 4 and you'd be like, oh, it's not here, so it'd be undefined. Okay? All right, let's move on to the next one. This one has 3 pieces. It won't hurt you. It's kind of fun. And I'm going to graph the first piece and the last piece first. So let's see. Graphing f of x equals -3. So y equals -3 is a horizontal line down here at -3. And if you want to graph way too much and be like, oh no, I graphed way too much, that's fine. But I'm not going to get too carried away with it because the only x values that I need are the ones that are less than -3. So here's -3 and less than -3. There we go. Less than -3. So we're going to keep this and erase everything else. There we go. And not equal. So circle here where x equals -3 and y equals -3. And we'll go here. And notice that this is just straight up less than -3. Actually, straight horizontal. Less than, bad pun. Less than -3, meaning it just goes forever and ever and ever and ever. And there you go. Okay, I'm going to graph this last piece. It's 3. So 1, 2, 3, horizontal line, doo-doo-doo-doo-doo-doo. But I only want to keep the parts that have x values greater than 3. So from here and forward, and everything else gets erased. There we go. Okay. Now we'll graph this middle piece, and this is y equals mx plus b. Well, m is -1, so our slope is -1. Our y-intercept is 0, so dot here. Down 1 over 1, down 1 over 1, down 1 over 1, and we can just keep going with this, and we can keep going in the opposite direction as well. Back 1 and up 1. And we have this line right here. I would like to explain this inequality that's happening here. And I didn't explain it much here other than to slap my hands down, but this is what it really means. I'm going to read it in pieces. We're going to say that -3 is less than or equal to x. Okay, well that's kind of backwards. -3 is less than or equal to x. What that really means is that if you take just this piece right here, you don't have to circle it, but if you take that piece and just read it backwards, you'd have x is greater than or equal to -3. So I need the x values that are greater than or equal to -3. So we could just start and say, well, I know that much. At -3, we're going to have a circle, and I don't need that. That's too much. Okay? And we also have this piece. X is less than or equal to 3, and actually the mathematical word that goes with this is and. So I need all the x values that are greater than or equal to -3, or, I'm sorry, and, woo, wrong word, and x is less than or equal to 3. Let me say it again and try to get it right this time. I need all the x values greater than or equal to -3, and they're also less than 3, and that's why it's between those two values. So I'm thinking of a number, it's greater than -3, and it's less than 3. Well, then I can pick any number from here to here. It's that kind of thing. There's an overlap of everything that is greater than this and less than that, and it's the numbers in between. And so this is my graph. Okay, so back to the first conversation we had, the really first one, not the one about the pencil being old, but the conversation about graphing on Desmos, and here's the trick with Desmos. When you graph it on Desmos, if you can remember all the jargon for it, which is kind of a coding issue, which is practical, but you know, this is, in my opinion, a little bit more practical in terms of finding the circles and open and closedness. That's the point of what I was going to say. When you graph it on Desmos, it doesn't always show up the open closed circles. It's really tricky, so you still have to have the skills to know, well, this piece corresponds to an open circle and this piece corresponds to a closed circle. Okay, let's do these last two here. And actually the last one is super duper easy and the next one is not. So we're going to graph this parabola. We're going to graph a parabola. Let's see what we have here. We've graphed this kind of stuff before. This parabola only exists for x values less than 1. So let's just go ahead and say this is it. Here's 1, and I'm just going to graph over here. If I go too far, I'll have to erase something, right? And this line is only going to exist here, so if I graph this, I'll have to erase it and just keep that part. There was a lot of hand waving. You'll see what I mean. So this is a line. No, it's not. It's a parabola. Sorry, this is a line. This is a parabola. We're going to shift it up 3. 1, 2, 3. And normally parabolas open up like this. This one does not. It opens downward. You have seen these kinds of transformations before. There's a whole lesson devoted to this later. It's the next lesson. And if you would like to, and you should, you totally should, you may want to make a little table of values, or at least do it in your head. Here's what I'm going to do in my head. If I plugged in a 0, I'd get 3. If I plug in a 1, I would have 1 squared, so 1 times -1, so -1 plus 3, which would be 2. Or if I plugged in a -1, I'd have -1 squared, which is 1, times -1, which would be -1 plus 3, which is 2. I can plug in a -2. I can't plug in a +2, see? But I can plug in a -2, plug in a -2, and I'll have, let's see, -2 got squared, it became +4. Let's do it. -2 got squared, then we'll have to change the sign of that. So this would be +4, but it becomes negative, and so -1. So -2 has an output of -1. And then plug in a -3. When we plug in a -3, we're going to get 9. So -9 plus 3 is going to be -6. So at this point, we're off the grid. So this, off grid, like you make your own electricity. That's a bad joke. Here's our parabola. And if you're like, man, I can't get my parabola to look like that. Well, good, because mine looks terrible. But it keeps going to the left. I know you're like, man, but it's going down. I know. I'm kind of looking ahead to a domain and range lesson here. If I wanted to talk about what this graph is doing, I could say, oh, this graph is going down, yes, but this graph is also going to the left. Like, it goes forever this direction. It is going down faster than it's going to the left, but it is going to the left. Like, this graph exists here. I just have to go way down to get it, okay? All right, let's put a circle here and talk about what happens. All right, let's talk. Should I fill that circle in? No, it's an open circle. Okay, something tricky is about to happen though. I'm about to fill that circle in, and here's why. This equation, the line, is going to touch at that point. So there are times where the points will be broken. Let me rephrase that. Your piecewise function will be broken. That is not the official word for it. The actual official word is discontinuous. Oh, we haven't read the directions, have we? Ha ha. We just added 20 minutes to this video. Ha ha ha. No, I'm kidding. All right, what we're going to do is graph this, and we'll talk about what a discontinuity is, and it's not going to be that bad at all. So this line is y equals 3, your y-intercept, your slope is -1, so I would go down 1 and over 1, and here's my line. I'm going to draw it very faintly. There's my line. Isn't that nice? But I only want this graph to exist for x values greater than or equal to 1, so keep that. Keep that right there. Keep that right there. It's there. Keep that there. And then I'm going to erase this itty-bitty little thing that you can probably barely see on your screen, but there's a tiny little line that was interfering with my parabola. But now we have this issue where the parabola did not equal at 1, but the line does. But they both meet at the y value of 2, so what was an open circle gets filled in. Okay? So let's talk discontinuity. If I wanted to graph this graph, could I do it without lifting my pencil? Yes. Now there's a little bit of a shift here, but I never had to lift my pencil, right? And I could just keep going. So this one has, what color should we use? You choose. What color do you want me to write with? This one's black, by the way. Black, green, purple, red, blue. What color? Okay, I will. This one has no discontinuities. However, the other two that we've already graphed do have discontinuities, and those discontinuities are going to occur here, where I would have to lift my pencil or pen, and also here, where I would have to lift my pencil or pen. Now, if you're looking at this and saying, is that a discontinuity? Is that a discontinuity? No, that's just the end of my graph. Like, I'm going to start graphing now. That doesn't make this a discontinuity. But as I begin to graph this and I get to this point, I'm like, oh, I got to, there we go. So the very basic definition of a discontinuity is where your function is discontinuous. I mean, really, it's the definition is kind of in the word. We'll write that down in a minute. So I have a discontinuity at x equals, okay, I like to give the x value where this takes place. So when I lifted my pencil pen, whatever you're using. I did it there. Okay, where is there? Let me ask it a different way. At what x value did I pick up my pencil? The answer is 0. Now, the y values were down here, but the x value was 0. Okay, so let's do this one also. By the way, I get tired of writing discontinuity. I've written it twice already in different forms. And so I will abbreviate it, and it is totally acceptable mathematically, at least in my class, to call it a disco. Because, hey, I was born in the 70s. So disco at, all right, da-da-da-da-da-da-da-da-da-da, whoop, pick that pencil up. And I had to pick that pencil up or pen up at -3. So disco at x equals -3. And still drawing. I wonder when I'm going to have to pick my pencil up again. Now! Ooh, and now occurred at x equals +3. So at x equals -3 or +3. If you want to do the plus or minus thing, you could. All right, let's graph this last one, talk about some discontinuities. I might give a formal definition for it, or at least a rough definition for it, so Mr. Williams can be proud of me. And then we will be done with this graph, and then I will show you in another video how to graph these on Desmos. So f of x equals 2. Oh no, I graphed too much. I want to keep everything that is less than 2. Now, let's not get confused with the 2's going on here. The y value is 2, but I want to keep all the y values at 2 when x is less than 2. So x is less than 2 here. I will keep everything where the x values are less than 2. So this stays. This does not. Okay, -2. X is greater than or equal to 2. So my y value is -2. Oh no, I graphed too much. Mr. Williams is just going to walk in and grab the pencil from him and be like, "You're wasting lead." Mr. Williams, I've not seen you in so long. I know, but you're wasting lead. X is greater than or equal to 2. Keep this part. Don't tell Mr. Williams. He was principal at my elementary school for a long time. He was there my 7th grade year. I think he came my 7th grade year. You don't care, but I'm telling you anyway. Or maybe it was my 8th grade year. By the way, I didn't go to a middle school. I went to a K through 8 school. And he stayed for, oh my goodness, a long time afterwards. I don't remember how many years. Anyway, all right, there's an open circle, there's a closed circle. There's not always an open circle and a closed circle, but in this case, there is a closed circle. Sometimes they're both open, and you're like, oh, what happens at 2? Well, that would be undefined, just saying. Okay, if the graph looked truly like this, then the y value at 2 is, well, there is no y value at 2, so it would be undefined. But let's finish graphing it. At x greater than or equal to 2, greater than or equal to 2, that'd be this piece, and so we will fill that one in. So we do talk about discos, and if I had to lift my pencil, I would lift it at x equals 2, so we have a disco at x equals +2. By the way, discontinuity doesn't have to look like this. It could look like da-da-da-da-da-da-da-da, boing, doodle-doodle-doo, and you keep on going. There's a hole in your graph, actually. That's going to happen later. So this word discontinuity, I'm going to erase that because it's not relevant to what we're doing at the moment, although we could totally have a piecewise function that does that, but they're not on this page. This word is going to come in handy later when we graph these things called rational functions. In the meantime, let me pick a color, green, and I am going to give you a very rough definition of a discontinuity. This is not a textbook mathematical definition. A discontinuity is an x value. This is going to work for this lesson, and then we'll get into more detail later. An x value where the graph is not connected and I could leave it at that, but I want to say more even though I'm not going to write more. Or it could have a, like I did where I erased it, a hole in the graph. That's an issue we will address later.